There is a very
Something is flying through our solar system right now that does not belong here. It did not form around our sun. It was not born in the Kuiper Belt or the Oort cloud or anywhere else in the familiar territory of our planetary neighborhood. It came from somewhere else entirely, from interstellar space, from a region of the galaxy so ancient and so distant that the object itself may be nearly twice as old as the Earth. It passed close to Mars. It swung around the sun. And now it is heading back out into the void between the stars, carrying with a set of properties so unusual that nearly 100 scientific research papers have been published trying to make sense of what it is and where it came from. Its name is 3I Atlas. The 3I stands for Third Interstellar Object, the third visitor from beyond our solar system that humanity has ever detected. And while the first two interstellar objects we identified were remarkable enough in their own right, 3I Atlas is different. It is bigger. It is faster. It arrived from a completely unexpected direction, and it has behaved at virtually every stage of its journey through our solar system in ways that do not match anything in our catalog of known cometary behavior. The scientific community is genuinely puzzled. The public conversation has been, predictably, considerably more dramatic. Today we're going to cut through all of it, the speculation, the noise, and the breathless headlines, and give you a clear, honest account of what 3I Atlas actually is, what we actually know about it, what genuinely remains mysterious, and why this object matters regardless of how the remaining questions eventually get resolved. The discovery of 3I Atlas followed a path that has become increasingly common in modern astronomy, a wide-field automated survey system scanning the night sky for moving objects flagged something unusual, and human scientists then worked backward from that detection to understand what they were looking at. The detection came on the night of July 1st, 2025, courtesy of the Asteroid Terrestrial Impact Last Alert System, a network of telescopes distributed across multiple continents, including installations in Hawaii, Chile, and South Africa. The system's purpose is exactly what its name suggests: to monitor the sky continuously for objects that might pose an impact risk to Earth. It does this by tracking moving objects, anything that shifts position against the background of fixed stars from one observation to the next, and flagging them for further analysis. The object spotted that July night was logged initially as a new asteroid. This is routine. The survey systems detect new asteroids on a regular basis, most of which turn out to be unremarkable members of the solar system's existing population. Classification, cataloging done. But when astronomers look more carefully at this particular object, they notice something that immediately elevated it from routine to extraordinary. It was moving too fast. Speed is one of the most fundamental pieces of information you can extract from observing a solar system object. Everything in the solar system moves. The planets, the asteroids, the comets, all of them are in constant orbital motion around the sun. The speed at which an object moves is directly related to its distance from the sun and the nature of its orbit. Objects in closed, gravitationally bound orbits around the sun, every planet, every asteroid, every comet that originated in our solar system, move at speeds that are consistent with that gravitational relationship. There is a specific threshold velocity, called the hyperbolic excess velocity, above which an object cannot be gravitationally bound to the sun. If an object exceeds that velocity, it is not in orbit around the sun. It is passing through. When astronomers calculated the velocity of the newly discovered object, the number they got was 58 kilometers per second. For context, Earth orbits the sun at approximately 30 kilometers per second. Mercury, the fastest planet, moves at around 48 kilometers per second. The new object, detected at a distance of roughly 4.5 astronomical units from the sun, just inside the orbit of Jupiter, was moving faster than Mercury despite being far further from the sun. The math was unambiguous. This object was not bound to our sun. It had come from interstellar space, and to interstellar space it would return. This was the moment 3I Atlas received its designation, the third interstellar object ever identified. It joined a select and very short list. To appreciate what makes 3I Atlas significant, it helps understand the two interstellar objects that preceded it, because the differences between all three tell us something important about the diversity of objects traveling between star systems. The first interstellar object ever identified was Oumuamua, detected in 2017, and it remains one of the most debated and puzzling objects in the history of solar system science. Oumuamua was unusual in almost every measurable way. It appeared to have an extremely elongated shape, perhaps 10 times longer than it was wide. Unlike any known solar system object, it accelerated as it left the solar system in a way that could not be explained by gravitational forces alone, suggesting some kind of non-gravitational propulsion. It showed no signs of the cometary activity, the coma and tail produced by sublimating volatile materials that would typically be expected from an object of its type heating up as it approached the sun. Oumuamua generated an enormous volume of scientific literature and considerable public speculation about its nature, some of it from serious scientists who acknowledged that the most exotic explanations could not be entirely ruled out. The second interstellar object, Borisov, discovered in 2019, was in many ways Oumuamua's opposite, despite being interstellar, moving on a clear hyperbolic trajectory indicating an origin outside our solar system. Borisov behaved almost exactly like an ordinary comet from our own solar system. It developed a coma and tail as it approached the sun. Its chemical composition was broadly consistent with solar system comets. Its shape appeared roughly spherical and unremarkable. If not for its velocity and trajectory, Borisov might never have attracted particular scientific attention. The interstellar middle child, interesting primarily for confirming that not all interstellar objects are bizarre. 3I Atlas sits in an entirely different category from both of its predecessors. It is substantially larger. Estimates suggest it could be up to 5.6 kilometers in width, making it several times larger than Borisov and far larger than the sub-kilometer Oumuamua. It is traveling at roughly double the velocity of either predecessor, and it arrived from a direction that neither of the first two interstellar objects shared, not from the general direction the solar system is moving to the galaxy, as Oumuamua and Borisov largely did, but from the direction of the galactic core, arriving in almost perfect alignment with the plane of the ecliptic. The solar system's planets all orbit the sun in a relatively flat disk, the ecliptic plane, and 3I Atlas arrived at an angle of only 3 degrees off from that plane. In a three-dimensional universe where an incoming object could arrive from virtually any direction, that alignment is a striking coincidence. The question of where exactly 3I Atlas originated is one that astronomers have been working hard to answer, and the picture that has emerged is both fascinating and genuinely humbling in terms of the distances and timescales involved. The direction of 3I Atlas's incoming trajectory points back toward the galactic core, the central, densely packed region of the Milky Way, where stars are far more tightly concentrated than the outer spiral arms where our own solar system resides. But pinpointing a direction of origin is only the beginning of the problem. Space is three-dimensional. Identifying where in the galaxy an object actually formed requires working backward through its entire trajectory, accounting for the gravitational influences of every star it has passed near, the overall rotation of the galaxy, and the relative motions of different stellar populations over billions of years. Astronomers have managed to trace the trajectory of 3I Atlas backward in time across approximately 10 million years of travel, and during that period they have identified 93 stars that the object passed close enough to have interacted with gravitationally. The closest of those encounters involve a star at a distance of approximately 0.3 light-years, about 63,000 astronomical units, a vast distance by any human standard, but a relatively close shave in galactic terms. The broader analysis of 3I Atlas's origin places it most likely in the thick disk of the Milky Way, a component of the galaxy distinct from the thin disk, where most of the galaxy's star formation and spiral arm structure is concentrated. The thick disk is an older, less chemically enriched population of stars occupying a broader vertical extent above and below the galactic plane. Objects in the thick disk have tended to be undisturbed for very long periods of time, which has led astronomers to estimate that 3I Atlas could be as old as 7.6 billion years, nearly twice the age of Earth and roughly half the age of the universe itself. If that age estimate is correct, 3I Atlas formed around a star that no longer exists in anything like its original form, in a planetary system about which we know absolutely nothing, in a region of the galaxy that was already ancient when our own solar system was just beginning to take shape. It had been traveling through interstellar space for billions of years, encountering 93 stars without coming anywhere near as close to any of them as it is currently passing to our sun. Whatever it is made of Whatever processes shaped it, it carries information from a time and place in galactic history that no other form of observation can access. Once 3I Atlas was confirmed as an interstellar object and scientists began pointing their most powerful telescopes at it, the measurements they collected told a story of an object that behaved unlike any comet previously observed at virtually every stage of its approach. The first anomaly became apparent through data from the Transiting Exoplanet Survey satellite, an orbital telescope that happened to be observing the region of sky through which 3I Atlas was passing during May and June of 2025, before the official discovery date. During this period, as the object was still well beyond the orbit of Jupiter at distances greater than 5 astronomical units from the Sun, its brightness was already increasing far faster than expected. Astronomers had predicted the flux, the perceived brightness, would increase by a factor of about 1.5 as the object moved closer to the Sun over those weeks. What they measured instead was an increase by a factor 5. Something was already dramatically brightening the object at distances where typical solar system comets remain largely inert and frozen. The explanation became clear when spectroscopic analysis of the light coming from 3I Atlas revealed the composition of its coma, the cloud of gas and dust surrounding the object. In typical solar system comets, the coma is dominated by water vapor, with carbon dioxide and carbon monoxide present in much smaller quantities. The ratio of water to carbon dioxide is usually something like 8-to-1 in favor of water. 3I Atlas had this ratio almost completely inverted. Its coma was dominated by carbon dioxide at a ratio of approximately 8-to-1 in favor of CO2. This single observation explained the early coma formation. Carbon dioxide ice sublimes at much lower temperatures than water ice, meaning 3I Atlas began outgassing vigorously at distances where water ice would still be completely frozen solid. The object was essentially behaving like a ball of dry ice exposed to mild warmth, beginning to generate gas and reflective cloud long before the Sun's energy was strong enough to melt its water component. As 3I Atlas moved closer to the Sun and temperatures increased, the water component of its coma began to assert itself. By late September, as the object was passing through the inner solar system near the orbit of Mars, it was releasing water vapor at a rate equivalent to a high-pressure fire hose running continuously, more water than would be expected from even a typical solar system comet at that distance, and a reversal of the earlier CO2 dominance that happened faster and more dramatically than scientists had anticipated. The metallic content of the coma produced its own set of puzzles. Early observations detected nickel in the cloud surrounding 3I Atlas, but found no iron. Anomalous because nickel and iron are produced together in stellar nucleosynthesis and are almost always found in comparable proportions in solar system bodies. The eventual appearance of iron in late September, followed by a rapid normalization of the nickel-to-iron ratio toward more typical values, suggested that some process had initially separated these elements, possibly the early CO2 outgassing dragging nickel atoms along, while iron remained temporarily locked in the surface material, before the increasing solar heating released iron as well. Among the most visually striking anomalies in 3I Atlas's behavior was the orientation of its tail during the early phases of its solar approach. Comets develop tails through a straightforward physical process. The solar wind, the constant stream of charged particles flowing outward from the Sun, interacts with the gas and dust in the comet's coma and pushes the lighter material away from the Sun. This is why comet tails always point away from the Sun, regardless of the direction the comet is traveling. It is one of the most reliable visual signatures of cometary activity. During the summer months of 2025, as 3I Atlas was still approaching the Sun from beyond Jupiter's orbit, observers noticed something that initially defied explanation. The object appeared to be developing a sun-facing tail, material accumulating on the side of the coma pointing toward the Sun, rather than away from it, a comet with a tail pointing in the wrong direction. The eventual explanation is connected to the object's unusual composition and the early onset of its outgassing activity. Because 3I Atlas began sublimating carbon dioxide at such a large distance from the Sun, the solar wind at that distance was not yet strong enough to push the accumulating gas and dust cloud away efficiently. Instead of being swept back into a conventional anti-solar tail, the material was piling up on the sun-facing side of the object, creating the anomalous forward-pointing feature. As 3I Atlas moved closer and the solar wind strengthened, the conventional tail geometry eventually reasserted itself, and by September a short fan-shaped tail pointing away from the sun had developed, unusual in shape compared to the long, streaming tails of famous comets like Hale-Bopp, but consistent with the object's distance from the sun and the specific materials being sublimated. The closest 3I Atlas came to any planet in the solar system was a pass within approximately 0.19 astronomical units of Mars in early October 2025. This proximity was scientifically valuable because humanity maintains a substantial fleet of instruments in and around Mars, orbiters, surface rovers, and landers that could be turned toward the visiting object. Images captured by NASA's Perseverance rover from a Martian surface showed 3I Atlas as a streak of light in the Martian night sky, not a crisp resolved image, but photographic record of the object visible from another planet's surface, a genuinely remarkable achievement. Images from the European Space Agency's Mars orbiter provided additional perspective, though at insufficient resolution, to distinguish the object's nucleus from the surrounding coma. Following its closest approach to the sun in late October 2025, 3I Atlas passed behind the sun from Earth's perspective and remained unobservable for several weeks. When it re-emerges into observational range in December, scientists will have the opportunity to study how its properties have changed following maximum solar exposure, what the sun did to its surface, how its activity level evolves as it begins cooling on its outbound journey, and whether any new features or behaviors emerge in the post-perihelion phase. The final significant event in 3I Atlas's solar system passage will be a relatively close approach to Jupiter in March 2026, with a spacecraft Juno, which has spent years studying the giant planet and its moons, may have the opportunity to image the departing visitor one last time before it recedes into the outer solar system and eventually back into interstellar space. The scientific importance of 3I Atlas cannot be overstated. Every interstellar object that passes through our solar system carries information that cannot be obtained any other way. Direct physical samples, in the form of the gas and dust released into the coma from a planetary system entirely separate from our own. The unusual chemistry of 3I Atlas, its carbon dioxide dominance, its anomalous metallic ratios, its extreme light polarization, its early coma formation, all tell us that the solar system it came from was different from ours in ways that matter. Different volatile ratios, different formation conditions, different chemistry. The universe does not make all planetary systems the same, and each interstellar visitor that passes through provides a data point in the emerging picture of what that diversity actually looks like. 3I Atlas is almost certainly not the last such visitor we will detect. Improved survey systems and better detection technology mean that we are increasingly likely to identify future interstellar objects earlier and track them more thoroughly. The three we have found so far, Oumuamua, Borisov, and now Atlas, have each been dramatically different from the others, suggesting that the population of interstellar objects traveling to the galaxy is every bit as diverse as the population of objects in our own solar system. We are, for the first time in human history, beginning to read the mail that the galaxy sends us through these ancient wandering messengers. 3I Atlas is the most recent letter. It is strange, complex, and not yet fully decoded. But the fact that we can read it at all, that we have the telescopes, the instruments, and the scientific understanding to extract meaning from the brief passage of a 5-kilometer object traveling at 58 kilometers per second through a solar system it will never visit again, is one of the more remarkable things our civilization has ever managed to do.